Hi, so today we're going to be going over Physics Lab 1, and this is by Ateendra Subramanian. So, our intro and what we wanted to get out of this experiment was how does one-dimension kinematic equations predict real-life kinematics experienced by us? So, key physics concepts involved was we tested Newton's first law, which says an object at rest remains at rest, and an object in motion continues moving at constant velocity in a straight line unless acted upon by a net external force. In order to do this, we used basically two very important equations, which was one, V average equals displacement over change in time, and then we used R final equals R initial plus V average delta T. And so some key assumptions we made in this experiment was that no air resistance or friction were involved, and the table is completely flat. And we'll discuss this more in our error section. So what we found, overall, the Newton's first law did a great job predicting the position of the experimental mass that we used. However, it was still slightly inaccurate, and that's due to errors we'll be mentioning in the upcoming sections. So yeah. Exact concepts we were testing, we were aiming to see whether Newton's first law was followed in our live experiment. To do this, we rolled a mass with constant velocity along the x-axis. To find average velocity, we used the formula below. R final minus R initial over delta t equals average velocity, like we mentioned in the previous section. And then using the calculated average velocity, we plugged into the formula R final equals V average delta t. We then compared the actual results with the results we obtained from the kinematics equation above. So, in order to carry out our experiment, we used our arm or our hand to create an initial rolling mass in the plus x direction. Using the tracker app, we calibrated the total distance, and we were able to track displacement over time. We'll mention that in the coming sections. And then using the computational software, we measured the displacement according to ideal conditions. And so the exact stuff that we used was a meter stick, a rolling mass. We used our hands for initial velocity, the table, and then the computational software. So let's go over the system and surroundings now. The system was the rolling mass, the surrounding was everything else in the experiment, including the table, and then we put an initial force, but after that, no significant forces were acting on the object. Okay, so now let's go ahead and let's explain the models. So in our real-life experiment, we used our hands to roll the rolling mass in a straight line in the plus x direction. You can see that here that using the tracking software right here, we cut out the beginning when our hand rolled the mass and the end of the trial to obtain 15 frames, which lasted 0.233 seconds. You can see the individual frames by the red dot. Because the surrounding forces are negligible, we can use Newton's first law to assume a constant velocity. The tracker software calculates the position each of the frame and shows us the time as well. And you can see that each of the red frames were the center of mass of the mass, and then this shows the position. And then we were able to calibrate it using the tracking software, and then so you can see the ruler stick in the background, and using that ruler stick we were able to calibrate the whole meter stick, so it should give an accurate prediction of where it is at that point. And then in order to find our V average, we got the final position, which is 0.129. We subtracted from the initial position, which you can see here, and then we divide by the total time. And we got an average velocity, which will be used for our computational modeling. And basically what the computational modeling does is it just uses this equation, the final position. So here is our glow script computational modeling. You can see the vector, you can see the velocity, you can see the change in time that we used, you can see the total time right here, and then basically this just updates the velocity and position. The velocity doesn't really change, but it updates the position in each of the time intervals that were the same as the ones we did manually in our actual experiment. And then from the computational model, you can clearly see that it changes in a linear format. Furthermore, the velocity is constant throughout the trial due to no surrounding forces, and that's exactly what Newton's first law says. So here are the comparisons, and so in our x real versus x predicted, you guys can pause it and see it, but it's very similar, but the x real does differ from the predicted in certain amount of times, and then once again you can see this in our graphical comparison. So source of errors, why is it different? Weirdly, in our actual experiment, the position sometimes falls behind the predicted value and then gets ahead, and this may be due to the surrounding forces on the ball. We might conclude that the table isn't perfectly flat, allowing for gravity to have an effect, and then when we roll the mass, we might have put some force in the y direction, leading to an error in calculation. So what happens if additional force is added, and how would the experiment change instead of rolling and we let it drop from a certain point? Then there would be gravity acting as another force, and we would have to take that into account gravity was force, then velocity would change throughout the trial, and we'd have to use this equation into account, where F net over m would probably equal negative g, which is negative gravity. And so, to wrap it up and our final conclusions, it's hard to test Newton's first law due to the many surrounding forces that are apparent in a physics classroom. We can test the ideals on computational software, but it's very hard to do in an actual experiment. Nevertheless, our results were extremely close, proving that even though there were some forces, his general theory held true in our experiment.